So this talk is about a system in which a client can verify the correctness of a remote execution. Suppose that there is a well-provisioned server in the cloud that executes a large MapReduce job on behalf of a client. Once the job finishes, the client might like to know if the server computed correctly. Because there are lots of sources of incorrect execution, including corruption of data, either in storage or in transit, that could result in an incorrect output. As a result, we would like to build a system in which a client could be given confidence in the correctness of outputs. There are powerful theoretical results based on complexity theoretic tools like probabilistically checkable proofs, which say that the server can create a short proof, and then the client can check the short proof to know if the server computed correctly. This check does not make any assumptions about the failure modes of the server, and in principle, this check is very efficient. But that is only in principle. These theoretical solutions are not even remotely practical. However, recently, several projects have refined and implemented this theory. For instance, these recent works reduce checking costs by over 20 orders of magnitude. They also include compilers to transform C programs into executables that run verifiably. Unfortunately, despite this massive progress, these systems have severe limitations, which results in major roadblocks in bringing the theory to practice. First, the computational model supported by these prior systems is essentially a toy. They only support stateless computations. As a result, when a client outsources its computation to the cloud, the client has to supply all inputs to the computation and fetch all outputs from the server. Second, the client has to incur a large setup cost for every computation. Third, the server's work is still way too expensive. This brings me to the research that we did. We built a system called Pantry that addresses the first impediment. In addressing the first, we mitigate the second one by enabling new applications for which this restriction is acceptable. Unfortunately, we retain the third limitation. Before I go further, I would like to address a nagging question. Aren't there more pragmatic approaches for this problem? At one level, the answer is yes. For instance, consider replication, trusted hardware, etc. But there are 2 points. First, these approaches make assumptions about failure modes of the server. For instance, replication assumes that there are replicas and their failures are largely uncorrelated. As a long-term goal, we want a system that makes no assumptions about the failure modes of the server, and Pantry should be seen as a step towards that goal. Second, Pantry enables applications for which there are no pragmatic alternatives. For instance, as I'll show you later, Pantry enables applications in which the client can verifiably compute over the server's private state. The rest of this talk is in 3 parts. First, I'll describe prior verifiable computation systems that Pantry extends. Second, I'll describe how Pantry enables a notion of state in verifiable computation. Third, I'll describe how Pantry mitigates the issue with the client setup cost by enabling new types of applications. I'll do that in the context of applications that Pantry enables, along with a performance study. Both Zottar and Pinocchio accept programs expressed in a subset of C and transform them into 2 executables. The first executable runs on the server and generates a short proof, and the second executable runs on the client and checks if the server's proof is correct to know if the server computed correctly. But under the hood, this transformation process decomposes into 2 stages. In the first stage, computations are compiled into a low-level representation, which is a set of algebraic constraints over a large finite field. In the second stage, these algebraic constraints are combined with complexity theoretic tools like probabilistically checkable proofs and cryptographic primitives to generate 2 executables. So there are actually 2 interfaces here. One is the interface that's exposed to the programmers that accepts a subset of C. And second is the interface exposed by the complexity theoretic machinery that accepts programs expressed as a set of algebraic constraints. So I'll briefly describe how computations are transformed into a set of constraints first. So the way the compilers implemented by Zottar and Pinocchio work is that they take a program expressed in a subset of C, go through each program statement in sequence, and then output a set of constraints for each program statement. Here is one example transformation that just increments its input. On the top right, I have shown an equivalent set of constraints. So one of the properties of this transformation is that once the variables that correspond to the input and the output are fixed, the system of equations has a solution if and only if the output is actually correct. So to demonstrate this, let's consider two cases. In one case, let the input to the computation be 6 and let the output be 7. As you can see, the equations on the bottom left has a solution, namely x equals 6 and y equals 7. But on the bottom right, there is no solution because an incorrect output always results in an inconsistent system of equations. Here is another transformation for the operation y equals x1 not equal to x2. The game here is to identify a solution to these constraints such that both equations hold simultaneously. So we can consider two cases here. First, suppose x1 is not equal to x2. So in this case, y will have to be set to 0 because there's no value for the auxiliary variable m that can satisfy equation 1. Second, in the case of x1 not equal to x2, y will have to be set to 1 because otherwise there is no way to satisfy the second equation. So to summarize the first stage, computations are statically unrolled into a set of constraints, and the satisfiability of these constraints is equivalent to correct program execution. I'll now briefly describe how the second stage works. In the second stage, the server uses powerful cryptographic techniques and complexity theoretic techniques to convince the client that it actually knows a solution to this system of equations. So to do that, the server first finds a solution by executing the computation in the constraints model of computation. And it then encodes that solution as a highly redundant error-correcting code. So I'm not going to go into the details of how this encoding works or what it looks like, but the important thing is that the encoding is far too large and much larger than the number of steps in the computation. And another powerful property of this encoding is that it allows very efficient spot checks. That is, it is possible to check if the server really has a solution by reading this encoding at a small number of places. So to spot check the server's large encoding, the client creates a set of queries that encode locations at which it wants to inspect the server's encoding. So creating these queries requires the client to take a pass over the entire set of constraints of that computation. So this is what constitutes the client setup work. Note that the client setup work is much larger than the cost to run the computation because it has to go through each constraint. And this, an important property of this setup work is that it does not depend on the actual input and output of a computation. Additionally, the cost to check a short proof is much smaller than the cost to run the computation on its own. So the client can actually save resources by verifying multiple identical computations with potentially different inputs. So to summarize the second stage, the server creates a short proof to convince the client that it actually knows a solution to the system of equations that represent the computation. So validity of a short proof actually implies that the server knows a correct solution to the system of equations, which in turn implies that the computation was executed correctly. So this raises a design question. How could we actually use the complexity theoretic machinery of the second stage for verifying stateful computations? More specifically, what constraints could be generate in the first stage such that their satisfiability implies correct storage interaction? So to motivate Pantry's answer for this question, I'll start with a naive approach, one that Pantry does not actually implement. Suppose that the storage operation that we want to represent in constraints is reading from the server's disk. On the right side, I've shown a set of constraints that faithfully represent a read operation from the server's disk algebraically. But there are actually two problems here. First, these constraints are actually an algebraic equivalent of a giant switch case statement with constraint for every possible address in the server's disk. And this makes the solution too expensive to use. Second, even if we put the performance issue aside, this solution is not complete. For instance, it only provides a notion of volatile state. As a result, if the client wants to simulate a notion of persistent state, it has to keep a local copy of server's state. I'll describe how Pantry addresses these limitations very soon, but for a moment, let's step away from verifiable computation and consider untrusted storage. In the world of untrusted storage, the server state is organized as a set of data blocks in which data blocks are named by collision-resistant hash of their contents. Suppose that a client holds a digest and wants to read an actual data block from the server. It can ask the server to return a data block and check if the server actually returned the correct data block by computing a hash of the returned data block on its own. Suppose that this untrusted storage client wants to actually run a computation with remotely stored inputs. It can do three things. First, it fetches blocks from the storage server. Second, it checks the integrity of blocks using digest, and then it can run the computation on those remotely stored blocks. So what Pantry does is compile these steps into a set of algebraic constraints and then use the complexity theoretic machinery of Zotar and Pinocchio to verify that the server actually executes these three steps correctly. So there are two reasons why this is interesting to us. First, the client does not actually have to fetch these blocks from the server. It only needs to check a short proof to know if the server is actually executing these three steps correctly. Second, there are lots of works that use the abstraction of an untrusted block store to build higher-level primitives like an untrusted file system, verifiable RAM, etc. I'm now going to demonstrate how Pantry works with a very simple example. Suppose that the client holds a short digest of a block which is stored at the server, and the client wants to search inside that block for a short string. So to verifiably execute this computation on the server, the client first represents the substring search as a set of constraints. And inside these constraints, the client also encodes a set of hash checks that the server can satisfy if and only if it uses the correct data block. The main takeaway here is that the satisfiability of these constraints implies that the constraints corresponding to hash checks pass, which in turn means that the server is using the right set of data blocks. So to expose Pantry's notion of storage to programmers, we added two primitives to Pantry's subset of C. First, put block takes as input a block and adds it to the server state. Second, get block takes as input a digest and returns a block such that the cryptographic hash of the block equals the digest. Here is a simple piece of code that uses get block to fetch a block from the server state and increment an integer stored inside that block. I've also shown an equivalent set of constraints which includes encoding a hash function as a set of constraints on the right side. So this raises a design question regarding the choice of a hash function. Normally, we would use a hash function like short of physics, but short of physics involves doing many bitwise operations that are far too expensive to represent in Pantry's model of computation. So what we do is we use an algebraic hash function that has very efficient representation in Pantry's model of computation and has over an order of magnitude fewer constraints compared to that of SHA-1. So to summarize Pantry, we augmented the subset of C that prior system supports with two storage primitives. Then we modified the first stage of the prior systems to include hash checks in constraints that are satisfiable only when the server supplies the correct data blocks. And then we reuse the second stage of prior systems. So we implemented several applications that use Pantry storage primitives like a simple database, a random access memory, a MapReduce framework that works over remotely stored inputs, and even programs that compute over the server's private state. I want to emphasize that these applications were built entirely in Pantry subset of C, augmented with get block and put block. And the complexity theoretic machinery behind Pantry was completely hidden from programmers. In the next part of the talk, I'm going to describe two applications that also happen to mitigate the issue with the client setup costs. So Pantry mitigates the issue with the client setup costs in two ways. First, it enables a class of data parallel computations, specifically ones that work over remote state. For these computations, the client setup works are tolerable because there exist multiple identical computations over which the client can actually amortize its setup costs. Second, Pantry enables applications that compute over the remote state, compute over server's private state, sorry. For these computations, the client setup costs are tolerable because the client cannot, in principle, execute those computations on its own. So to demonstrate data parallel computations, we implemented a verifiable MapReduce framework. So the client, what the verifiable MapReduce framework guarantees is that the client is assured that its MapReduce job was executed correctly by the server without the client having to handle any data blocks used inside the computation. So the client starts with a simple, starts with a MapReduce computation expressed in Pantry subset of C. So to actually use the server-side state, the client wraps its map and reduce functions with code that translates between digests and blocks. To verifiably execute this computation, Pantry proceeds in a straightforward way. So it first it asks the server to execute a set of mappers, and it supplies a digest for each of those mappers. Once the server finishes executing the map phase, the client gets a set of output digests. It then verifies that the server computed each mapper correctly. The verification of the reduce phase happens in the exact same way, with a set of new digests. So to summarize, the client starts with a set of digests, and then finally gets back a set of digests that correspond to the output of the job. So if the client really wants to see the actual output of these computations, it can fetch it from the server and verify if it got the right set of data blocks by recomputing hashes on its own. Or it could use these output digests in a new computation. I'll now describe how Pantry supports hidden state applications. So to motivate hidden state applications, consider a scenario where the server has a list of photographs of suspects. And the client, for example, a surveillance camera, wants to verifiably look up if a candidate image matches an entry in the server's list. Our key idea here is that Pantry storage primitives, when combined with a cryptographic property provided by Pinocchio called zero knowledge, provides a candidate solution. Zero knowledge guarantees that the proof supplied by the server does not leak any information about the intermediate state of the computation beyond what is implied by the output of the computation. But there are a few wrinkles. First, the client in Pantry holds a cryptographic digest of the server state, and this could leak information to the client. So to address this wrinkle, we wrap Pantry's hashes with a cryptographic commitment scheme that hides the actual contents of digests. The second wrinkle is that we now need to encode this commitment scheme as a set of constraints, and most standard commitment schemes are expensive to represent as a set of constraints. So to address the second wrinkle, Pantry makes a slightly stronger cryptographic assumption that allows us to use a cheaper cryptographic commitment scheme. We implemented several examples to exercise this machinery, but the most important point here is that we were able to build these applications that provide strong guarantees to the client and to the server by writing programs in a subset of C supported by Pantry. In the remaining part of this talk, I'll briefly describe the costs and benefits of Pantry. We implemented a set of MapReduce computations and a set of private state applications to measure the performance of Pantry. We ran experiments with a local cluster of machines, and I'm going to use the data collected from these experiments to answer 3 evaluation questions. First, we'll look at when the client actually saves resources relative to locally re-executing the computation. Second, we'll look at the cost of supporting hidden state applications. Finally, we'll look at the cost of Pantry server relative to simply executing the computation natively. To answer the first question, we experimented with a MapReduce computation that searches for a short substring inside a large DNA string. We fixed the amount of data processed by each mapper to be 600,000 nucleotides and vary the total size of the input processed. This graph summarizes the client CPU costs. What this graph shows is that the client can actually save CPU resources relative to executing the computation on its own if the size of the job outsourced to the server contains more than 30 billion nucleotides. The 30 billion sounds a lot, but it's actually DNA of just 10 people. We found a very similar result even for network costs. I would like to point out this graph is actually an extrapolation, but the y-intercepts and the slopes of these lines were determined empirically using hundreds of machines to run the server. The reason this graph is an extrapolation is because Pantry server is expensive, which limits us to small-scale experiments. However, there are actually scenarios where the server's costs may not be a problem because there are no naive alternatives to Pantry, for instance, in the case of hidden state applications. Since there are no naive alternatives, I'll just focus on the costs. The good news is that the costs to the client are actually modest. But again, the bad news is that the server CPU costs are on the order of minutes, and the server also incurs large storage overheads. This brings me to the source of the server's overhead. The reason Pantry server is so much more expensive than native execution can actually be decomposed into 2 pieces. First, Pantry server has to work in this constraints model of computation, which imposes up to 3 orders of magnitude blow up relative to native execution. Second, for each algebraic constraint, the server has to execute several cryptographic operations, and these cryptographic operations can be up to 3 orders of magnitude more expensive than plain text operations. So overall, the server in Pantry can be up to 6 orders of magnitude slower than native execution. So to recap, Pantry enables stateful applications, and it also mitigates the issue with the client setup cost by enabling new applications like data parallel computations and hidden state applications, which the client cannot execute on its own. But unfortunately, we retain the third limitation. So before I summarize Pantry, I would like to describe prior work and future work in the area of verifiable computing. There are lots of pragmatic approaches that either make assumptions about the failure modes of the server or they give up being general purpose. In contrast, Pantry makes only cryptographic assumptions and is also fairly general purpose. There are also approaches that make no assumptions about computations or about failure modes of the server, but practicality was never an explicit goal in these theoretical works. However, 4 projects have produced experimental results that implement this theory. The first is our own prior work, which is the line of work that resulted in Zotar. The second is a project from Harvard that's based on a different strand of theory, namely interactive proofs. These works are far more efficient, but only apply for a limited class of computations, essentially for those computations that have lots of repeated structure in them. The third is by Microsoft Research Pinocchio. Pinocchio and Zotar use the same underlying error-correcting code, which is due to the Pinocchio authors. And indeed, Pinocchio is one of the bases of Pantry. The last is a very recent work of Ben Sassan et al., who provide verifiability to class stateful computations. But that system's costs are orders of magnitude worse than Pantry for the computations that we have looked at. Finally, none of these systems actually support a notion of remote state that Pantry supports. And this brings me to the next steps for the area. The biggest problem in the area is the server's overhead, and any new techniques to reduce the server's overhead will be a major contribution for this area. The second problem is the client setup costs. We found scenarios where the client setup costs can be tolerated, but avoiding client setup costs would be a major contribution. There are theoretical solutions for this problem, but they do not appear to be suitable for practice yet. Finally, Pantry's computational model is general, but it incurs large overheads for representing certain operations like storage operations, conditional control flow. So any new techniques to reduce the overhead in representation will result in great improvements in end-to-end costs. So to summarize, Pantry takes another step in bringing powerful theory behind verifiable computation towards practice. And we think that the machinery underlying Pantry or a variant of that will be a key tool in building future secure systems. I can take questions.
Okay, there's one question from the moderator. So we know that existing prototypes of a proof-based verifiable computation, including Pantry, are too slow to be yet practical. Are you aware of any theoretical limits of how much faster they can get?
So the question is, are there any lower bounds on the performance? I'm not aware of any lower bounds, and there is no indication that this cannot get any faster. For instance, one simple thing would be that the server could actually use hardware support to become faster. Like if the hardware implements these cryptographic operations that Pantry requires, it could actually become like orders of magnitude faster than what it is today.
Christian Gaschan from IBM Research. You have your computation model is one where you have some sort of pigeon C to exercise arbitrary computations, and you have benchmarked applications that are matrix oriented and so on. Yeah, and turns out these are not efficient at all. But on the other hand, there are cryptographic protocols for which you can have dedicated for dedicated functions, right? Not general expressive computation. Do you see some hybrid between these models?
So the question is, Pantry is general purpose, but sometimes it incurs large costs, but there are cryptographic protocols specialized for a set of computations, and is there a way to create a hybrid?
For example, if you're retrieving something from an authenticated directory, then there's much more efficient or if you're updating an authenticated directory, it's much more efficient, and there is many other things in between.
So the answer is yes. Like, it is definitely possible to create a hybrid between the two. For instance, one of our prior works called Allspice tried to combine cryptographic protocols. It actually combines Zotar and the second strand of theory, namely CMT, to select the most optimal protocol between the two for a given computation. So it's definitely possible that we could add techniques to the compiler to select between Pantry and other special purpose protocols, but we have not done that. We did that for a limited class of protocols like CMT and Zotar.
Thank you.
Thanks.
Matthew Fernandez from NICTA and UNSW. You listed these three problems, that one you've eliminated, one you've mitigated, and the other one you've retained. But the one you've retained, the performance overhead, you've actually made that significantly worse, haven't you? It looked like the overheads had got significantly worse through encrypting the data storage.
So could you repeat the last part?
Sorry, the three problems you identified, where
Okay.
you'd eliminated one, mitigated the other, and you've retained the overheads on the server.
Yes.
But the overheads are actually significantly worse than previous solutions, right?
So I'm not sure I'm getting the last part of the question. Like, are you asking like the performance of Pantry is worse than prior systems?
Yeah, it seems like you've traded off the overheads on the server for this stateful computation.
Okay, so the server's overhead can be like I said, it can be decomposed into two things. First is the cost of representing these operations inside the constraints model, and then the cost from the cryptographic machinery. So storage operations definitely incur large overheads in representation, but this was not done in prior works. Like prior works, like they do not support any notion of state. Like there was no way to encode state operations. And what Pantry does is it allows us to encode storage operations as a set of constraints. And there is definitely blow up in going from say read operation to a set of constraints. But there's no way to do that in prior systems, unless it uses some techniques similar to that of Pantry.
Okay.
So
Not sure
it
I
does not
agree,
make.
but maybe.
So what I'm saying is it does not make service performance worse than prior systems because we did not do anything to the second stage of the system.
Okay.
So we retain the performance of prior systems.
All right, maybe I'll talk to you offline about it. Thanks.
Fred Schneider, Cornell University. You didn't say anything about whether your scheme could handle non-determinacy or randomized computation at the server. Is that in the computational model, or is that something that needs future work?
So the question is whether our computation model can handle non-deterministic inputs?
No, at this, a server that makes non-deterministic steps, or a server that uses randomized computation, say, to be more efficient.
Okay. In principle, we could handle that, but that would require representing, say, the source of randomness inside constraints. For example, we could probably require the client to supply C to the random number generator, and then the server has to show that it's generating randomness according to some random number generator.
So then it's not random.
Yes. So sure, it does not currently support those types of computations.
Yeah.